Here we're going to look at the Friedel-Craft Acylation of Benzene, and the reaction is as follows. The reaction is the reaction of benzene with an acyl chloride, which has got the following structure: RCOCl, and what we get in this reaction is the hydrogen from benzene is lost. One of these hydrogens is lost and replaced by this RCO group, and the hydrogen in benzene tags on to the Cl to produce HCl. So my product of this reaction would be plus HCl. So we can see there that my RCO group here replaces the hydrogen, and the hydrogen in the benzene ring then goes off with the chlorine to form HCl. So you can see here, this is my electrophile. I'm adding an RCO plus group to the benzene ring. So what we need to look at is generating the RCO plus, which is called an acylium ion. And what we do here is we react the acyl chloride with aluminium chloride, which is AlCl3. And what in effect happens, if you were to show this mechanistically, is that the pair of electrons in the CCl bond is used to form a bond with the aluminium. So in effect we get a curly arrow that goes like this, and that then produces my acylium ion, my RCO plus, and we also get aluminium, this AlCl4 minus ion. Okay, so if I was writing this equation out, it would simply be RCOCl plus AlCl3, and that gives us RCO plus AlCl4 minus. Okay, and that's the equation that you would need to remember if you're asked to generate the electrophile in a Friedel-Craft acylation reaction. The mechanism here is that this sort of curly arrow is not required, but I've put that in there to show you how this new AlCl bond is formed. We may then be asked the mechanism. It's likely you'll be asked for the mechanism of this reaction. Remember again, the mechanism is an electrophilic substitution mechanism. And when benzene reacts with this electrophile, we're reacting benzene now with this electrophile, this RCO plus ion, it is important that the pair of electrons from the delocalized ring system, it attacks this carbon. Now please don't make the mistake of thinking that this happens, because now this carbon is forming a fourth bond, so it doesn't need a bond to break. This is simply it. You do not do that. Please do not show that bond breaking there. That then produces the intermediate species. Again, partial delocalized electrons there. The horseshoe, remember that the horseshoe should not extend beyond that dotted line. And we get the following. And as we've looked at with the nitration of benzene, this carbon-hydrogen bond now will break, and the pair of electrons that were in this bond here will be then given back to retain the delocalization stability. And that there is the mechanism of this reaction. Remembering again, it is an electrophilic substitution. So I've got a question there, a question underneath there of how we would answer a question based on Friedel-Craft acylation in an exam. It says, consider compound P below that has been formed by the reaction of benzene with an electrophile. So in the example that we've got in the below, we can see here that the R group is a CH2CH3. It says, give the two substances that react together to form the electrophile and write an equation to show the formation of the electrophile. Well, specifically the two substances here would be propanoyl chloride, and obviously we also need aluminium chloride as well. And it says then to write an equation for the formation of this electrophile. Well, it'll be CH3 CH2COCl plus AlCl3, and again this chlorine is going to join on with the AlCl3, and we get this acylium ion plus AlCl4 minus. It then asks for a mechanism for the reaction. Well, the mechanism is going to be exactly the same as this mechanism here, but we replace the R group by a CH2CH3. So that there is Friedel-Craft acylation, and it gives you an example of how this question could be asked in an exam.